So I wanted to take a look at why is this like, okay, so this is f of x, and I want to take a look at, I just copy pasted the stuff from Wikipedia. And I basically want to take a look at so remember Simon's, so we're basically Simon's problem. And so I left it where basically I said, you're kind of measuring the circuit, and at the end what you're getting is a every time you measure, you're getting a superposition of like of strings that contain like one particular result of the function, because you measure f of x, so you get one of those, and so you get, and then on the input side you get a superposition of the possible inputs, right? So for example, if you measure 101, then you would get superposition of, so then you would get like can I, so you would then get something like this, and then 101 plus 101, right? So this is basically what you what you would get, right? And I can separate that with dot, with a comma or whatever. So why don't whatever. So you get, right? So this is something then we can get rid of because we don't do anything with it. And that's what we end up with, right? And then what happens is we're applying Hadamarts. We're applying like Hadamarts to the, I would say, to the 3 qubits, right? It's not times 3. I don't know what notation to use, but we apply Hadamard to all the 3 qubits. And remember that what we get at the end is a string that, so at the end we get a string y that if multiplied by s bitwise modulo 2 equals 0. And so I said in the last video that, just try to recap for myself. So basically that the Hadamard is helping us to uncover that relationship, because at the end of the day, really what you're getting is you're getting exactly those numbers, those inputs that have the same output. And so you want to see what relationship they have. And so I was wondering, I wanted to basically just do one video where I zoom in into that step, and then we do it by hand Hadamard, then try to understand how that interference leads to that, to finding that number, that string y. So we can stay with this example, right? So we got 0, 0, 0, and we've got 1, 1, 0. So we've got these things, right? So what happens when you apply a Hadamard? We'll do this bit by bit. So we'll do this. We'll start with this bit, and then with this bit, and then with this bit on the rightmost side. So here we end up with 0, 0, 0 plus 0, 1, right? So this bit gets basically, this qubit gets basically duplicated with the phase of like plus. Now this is our state. So now we apply that to the Hadamard to the second qubit, and so that becomes, so it's, what I'm seeing here is this, the one pattern that you see is that like you've got the same term you start with, right? Is always in your new state. So you're always going to keep adding that. but then you have, and then you have a 0, 0, 0 again, but you have a minus 0, 0, 1. So this is this is the two terms added. Oh, what? No, wrong. What am I saying? Let's go back. No, I just forget what I said. So we're applying it to the second qubit. So this term turns into obviously this term plus this term, and this term turns obviously into this term plus this term. Mhm. Good. So now you've got these guys, and so now we gotta apply this to the to our first qubit. So and I probably should do this in the second in a second line. So I'm gonna in a new line. So I'm gonna keep that here. I'm just gonna expand on top. So this turns into this plus this. This turns into, of course, itself plus this. This turns, of course, into itself plus this, and this turns into itself plus this. So far, so good. So there's no, here there's no interference happening. Basically, well, yeah, I mean, you end up with all the possible combinations. In this case, that was a trivial one, but I mean, so that basically that's basically what you end up with. And now, we're gonna do this one. So, and it's with a combination of both that then there's some interference happening, and that leaves you with that string that kind of has a relationship with S. Um, but it's funny because it seems to nevertheless this relationship with S be independent. It seems to be native to what the Hadamard does, because it's independent of the fact that the outcome is equal. The fact that the outcome is equal, you only use to actually get those two particular states. So what you want to see is you want to see how do they interfere. So what this basically might be telling me is that that's basically the kind of interference you get when you apply a Hadamard gate to a superposition of two separate states. That you basically get I wonder if that holds. If that holds true. So let's see. So we'll start from the rightmost qubit, and you get the same term, but then you get this. Now this term turns into itself plus minus, because remember we're doing the second qubit now, and it doesn't turn into itself, it turns into this. Exactly. It's easier if I just follow this pattern by saying this term turns into minus itself plus this, and this term turns into minus itself plus that. Good. So we already see that there are some of the numbers here, right, that they cancel. But let's go through all the Hadamarts. So I'm gonna do then a last one here, and so this term turns into itself minus. So it's gonna be a plus because the sign changes. And this term turns into itself minus and plus. This term turns into itself minus, which is going to be a plus. This. And this term turns into itself minus plus this. So what have we got basically? What do we get that cancels out, that doesn't cancel out? So I'm gonna put the outcome here. I'm gonna hide the tools because it's gonna be easier for you to see. So I start from the term 0 and 0, and 0 and 0 is in both places, so that stays 0, 0, 0. That's like we got it 2 times. Let's start with it, and then let's do 1, 0, 0 minus 1, 0, 0, so they cancel out. I'm just gonna mark those ones with a little asterisk, so I know that I've used them already. Good. So 0, 1, 0 and 0, 1, 0, they actually are both positive. So you also get 2 times 0, 1, 0. 1, 1, 0. And 1, 1, 0. So basically, I mean, I think I can get rid of those 2 times because those things, when you normalize, it just doesn't make any sense anymore. 1, 1, 0. 1, 1, 0 is there. 0, 0, 1 is there. 0, 0, 1 is there. 101 and 101 get cancelled, and then 011 is in here. So I cancelled this one already, and this I already also used. I'm bad at this, but I see they only repeated themselves once. So, and then 111 is 111. So it's the only 2 that minus really were these ones in here. 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1. I mean, basically, when I play the Hadamarts, I'm getting a combination of all possible values. But I'm just getting different patterns of those phases, right? So in this case, I get a negative phase for 1, 0, 0 and for 1, 0, 1. When your when your starting point is 1, 1, 0. Okay. So you guys basically get this one, this thing. Interesting. And so do they, all of them, fulfill that? That obviously does. Because rather, remember that S, in our case, S was equal to 110, right? So for this works, so it equals 0. For this, it also works. One times one. No, for this doesn't work. Have I done something wrong here? Let me take a look at. So let me just save that for a second aside. Try to open Quirk in my bookmarks. Bookmarks. Because basically here I've got these. So if I take a look at the amplitudes here after the hard marks, yeah, something is wrong. I must have done something wrong because this is not like. So I'm just getting. Uh, how can I do that? I think there was a way to do that. Where it's like not to indicate measurement, but to indicate basically exactly sampling. Samples that shows click when the target keyword is 1 and controls are satisfied. Because I basically want to see. Yeah, but I wanna pause selection. I should do a pause selection. So if I'm assuming that I measure 101, right? 101. And I should do that post selection probably. 101. So here I'm measuring 101. And then that's what's. Yeah, but it's still after that Hadamard. I must have done something wrong. Because here it says 000 That's correct. That was my starting point. But then I must have messed somewhere by hand. And I should have used Quirk directly, but as you can see, by hand it's easy to make mistakes. So you got 000 and 110. So, and after that, So it's clear. So and after that we get 0, 0, 0, 0, 0, 1, and 1, 1, 0, 1, 1, 1. And I mean, it's basically this, of course, what I was expecting. Must have done something wrong. So if I keep that aside for a second, I go back to this. I mean, I'll just trash that. So can I edit? So just where did I get it wrong? I'll try to redo it, but so I mean, yeah, that's the that was the point. I was supposed to do it by hand, so I kind of could understand what's how is that interference? What is that relationship, right? Mm, and how does this relate to S? That's the whole point of doing this by hand. Let me try to quickly do that again without thinking out loud quickly. So that does this. That basically turns into this plus this, right? That's for the first qubit. For the second qubit, you get this, and this, and so for the third qubit, you get basically this plus for this third one, you get and for the last one, you should have here a superposition of the possible values positive 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, and 7. That's correct. For 1, 1, 0, you basically get let's start from so you basically get 1, 1, 0, 1, 1. Then at the second qubit, basically you get 1, 0, 0 minus 1, 1, 0, and then plus 1, 0, 1 minus 1, 1, 1, and then here you basically get 0, 0, 0 minus 1, 0, 0. You get minus. Oh, here's why I went wrong, because I didn't keep that minus exactly. Minus 0, 1, 0 plus 1, 1, 0. This is where I went wrong, exactly. I'm bad at this, as you can see. Here we got like 0, 0, 1. We're doing this 0, 1 minus 1, 0, 1, and then here we've got minus 0, 1, 1 plus 1, 1, 1. So yeah, so basically you cancel out all the minuses, so the only thing you get with at the end of the whole thing is 0, 0, 0 plus 1, 0 plus 0, 1 plus 1, 1, 1. So I've just done that by hand, fine. Got the same result finally. But then what's the... And they all four fulfill these, so that's the point. Yeah, I feel that video was useless. So what's the relationship between the Hadamard and this? This statement, right? Because to understand that, maybe I should understand what is the Hadamard relationship with the minuses. Where are all these minuses ending up, right? Because it seems to me, so your source, your starting point in this case, right, is 1, 1, 0. That's the starting point, and this gives you a negative sign. This gives you a negative sign for the following: 1, 0, 0, 0, 1, 0, 1, 1, and 0, 1, 1. And a positive sign, so negative sign, and a positive sign for 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1. That's your starting point. Because basically, if you do the XOR in those cases, if you do the multiplication in all those cases, you get 0. In all those cases, you get something that's not 0. Interesting. So what I could do is see if that holds for this is if you do the if that's in relation to 0, because that's then easy to see that, right? So okay, I'll probably have to do another video on this, and because I got something there. Let me bookmark that as well, so I can take it from here. So I'll call it Simon's problem. ED, because basically that's it, right? So it seems like the Hadamard, in this case, the Hadamard is kind of then discarding you the ones that, uh, of course, that don't work. I feel I might be getting a bit too lost with that. I'll maybe reread, try to reread that, but it has to do with the science, and it has to do with the action of the Hadamard. So basically, it could be any two, right? And there could be many S's in here, so there's not just one S. And so the idea is that there's that relationship. Yeah, there's that relationship. There's at least one S. It's there. That's exactly feels that's exactly what the Hadamard is doing. So the whole problem is trying to. I mean, this is giving me some more insights on how on what's the essence of the Hadamard, but it's probably useless to just dive into this. But I probably want to do one or two more videos on this, and then I'll just move on. Essentially, what the algorithm is showing you is how to manipulate the superpositions, so then you find things like that, right? Because you can basically, while measuring the output, you can then kind of select a subset of your superposition for the first register. So and that's kind of something you wouldn't be able to do classically just with one run, right? So okay, not sure where this is taking me though. Let's see.